All right, so hello everybody, welcome to my talk. My name is Haiming Jin. I'm the first author of this paper. I'm a PhD student from the CS department of University of Illinois at Urbana-Champaign. First of all, I really want to thank you all for staying until the very last paper presentation of this conference. And a little bit of advertisement to make about myself before I talk about the paper is that I will soon be on the job market. So please kindly consider me if you have any postdoc or faculty positions. All right, so let's go back to business. I'm basically here to present our work, incentivizing privacy-preserving data aggregation for mobile crowd sensing systems. And this is a joint work with my advisor, Professor Clara Narstad, and Professor Lu Su from the State University of New York at Buffalo, and also Ho Ping Xiao from State University of New York at Buffalo. So the name of our work, Inception, comes from the three major aspects that we consider in this work, namely incentive, privacy preserving, and data aggregation. So our motivation for doing this work is that we have all experienced recent popularity of mobile crowd sensing systems that utilize the public crowd equipped with various types of mobile devices, including smartphone, smartwatch, smart glasses, and so forth for large-scale sensing tasks. And one example of such mobile crowd sensing system is a US FDA-approved MedWatcher system, where the platform will require participating users to submit photos about medical devices, and then the platform is going to analyze these photos to help identify visible problems with the devices. So this system is basically used for post-market medical device surveillance, and other examples include crowdsourcing based smart transportation, indoor localization, noise level monitoring, and so forth. So participating in a mobile crowd sensing system basically is costly for individual workers. The cost comes from various aspects, including CPU, memory, and disk usage, power consumption, and in many cases, privacy leakage. So therefore, it's highly necessary to have an effective incentive mechanism that can compensate workers' costs so as to stimulate worker participation. And actually, in real practice, incentive mechanism is not an isolated module. It will interact with other mechanisms, including a data aggregation mechanism that can aggregate workers' data, and a data perturbation mechanism that perturbs the aggregated results to protect the workers' privacy. So therefore, the performance and the design of the incentive mechanism are going to be affected by these other components in the system. And the reason that we need a data aggregation mechanism in a mobile crowd sensing system is because individual workers' data are quite unreliable because of poor sensor quality, incomplete view, environment noise, lack of sensor calibration, and so forth. A data aggregation mechanism that can properly aggregate workers' data so as to cancel out the errors from individual workers is going to be highly necessary. And in many cases, it's desirable to have a weighted data aggregation that considers workers' reliability. And the incentive mechanism should also consider workers' reliability so as to select workers that can provide more reliable data. And this indicates that the incentive mechanism is affected by the data aggregation mechanism. And many mobile crowd sensing platforms not only calculate the aggregate data, but also publish the data such as treatment outcomes to improve people's awareness of effectiveness of new drugs and medical devices, or locations of physical objects like potholes and so forth to help people have accurate and timely localization of these physical objects. However, the publishing of such kind of aggregated data will give an adversary the possibility to infer a lot of personal and private information of participating workers, including health information, locations, and so forth. And therefore, the publishing of the aggregated data will incur privacy leakage to participating workers. This is exactly why we need a data perturbation mechanism that can perturb the data before publishing to reduce the privacy leakage. And although we add some perturbation to the aggregated data, the privacy protection is far from perfect. So the incentive mechanism should also consider to compensate the cost for the remaining privacy leakage. And this is exactly how the incentive mechanism is affected by the data perturbation mechanism. Therefore, in this work, what we do is that we provide the integrated design of mobile crowd sensing system framework called INCEPTION that consists of an incentive, a data aggregation, and a data perturbation mechanism. The framework of INCEPTION consists of a platform and a set of participating workers. The platform consists of 3 components, including the incentive mechanism, data aggregation mechanism, and also data perturbation mechanism, as mentioned before. So the workflow of our INCEPTION framework goes as follows. Firstly, the platform will announce the set of sensing tasks to the workers, and the workers will submit bids to the platform indicating the set of sensing tasks they are interested to execute, and also their bidding price for executing the set of tasks, and also their bidding price for unit privacy leakage. And based on workers' bids, the platform will select the set of winners, and then the winners will execute the sensing tasks and send the sensory data to the platform. After receiving workers' sensory data, the platform will calculate the aggregated results of every task, and then pays every winner according to a payment that's calculated by the incentive mechanism. So before publishing the aggregated results, the perturbation mechanism is going to add some perturbation to the aggregated result and publish a perturbed results to the community or society. So this is basically the overall workflow of our INCEPTION framework. Yes, we'll then continue to talk about our design details of the 3 components of the platform. So although the data aggregation mechanism comes after the incentive mechanism in this workflow, we'll introduce this first because it affects how the incentive mechanism is designed. So we'll assume that there are a set of workers in the system and the platform holds a set of tasks. And we use S to denote the set of, the set of workers selected by the incentive mechanism. And we use gamma I to denote the set of tasks that worker WI executes. We use xij to denote worker WI's data about task tau j, which is continuous, which is assumed to be continuous in our case. And we use xj to denote the aggregated result for task tau j. And so the data aggregation mechanism is simply a weighted aggregation method which is utilized in many state-of-the-art literature, where lambda ij is the weight of worker wi on the calculation of the aggregated result of task tau j. So in this work, we choose the specific form of lambda ij to be proportional to alpha j minus theta ij, where theta ij is worker's skill level for task tau j, which is defined as the absolute difference between expected value of the absolute difference between the data provided by worker I on task tau j minus xj star, where xj star is the ground truth about task tau j, which is unknown to the platform and the workers. So it will assume that workers' skill levels are the platform's prior knowledge because it can be inferred from workers' submitted data, and it can also be inferred from other factors, including prices of the sensors and workers' reputations and experiences, using methods proposed in previous works. So alpha j is a platform chosen parameter for every task, tau j, which is related to the accuracy guarantee that we will talk about later. So basically, our specific choice of lambda ij conforms to our intuition that it should increase with the decrease of the value theta ij. So yes, we'll actually skip all the analysis of the data aggregation mechanism and directly talk about some results. Firstly, we proved that for every task, our data aggregation mechanism can minimize the upper bound of this error probability, which is the probability that the absolute difference between the aggregated result of this task and the ground truth xj star is larger than or equal to alpha j. And this data aggregation mechanism satisfies that it can upper bound this error probability by this expression. And based on theorem 1, we have this corollary 1 basically tells us that for every task, our data aggregation mechanism satisfies that it can upper bound this error probability by beta j if this condition is satisfied. And we call this alpha j, beta j accuracy in our work. And this is exactly the condition that the set of winners selected by the incentive mechanism should satisfy to ensure alpha j, beta j accuracy for every task. So So yes, our incentive mechanism actually takes the single-minded reverse combinatorial auction with privacy cost, which we call PSRC auction as the auction model. In the auction, the platform acts as auctioneer and workers act as bidders. So firstly, the platform will announce a set of sensing tasks to workers, and then workers will submit a bid to the platform consisting of the set of sensing tasks that this worker wants to execute, and also BIS, which is worker WI's bidding price for sensing, and also BIP, which is this worker's bidding price for unit privacy leakage. So, and then based on workers' bids, the platform will select a set of winners, and then winners will execute the sensing task and submit the sensory data to the platform. So finally, the platform will send the payment back to the winners who execute the sensing tasks. Then the worker's utility is defined as follows. If this worker is a winner, its utility is going to be PI minus CIS minus CIP times epsilon, where PI is the payment that worker WI gets from the platform, and CIS is worker's cost for sensing, and CIP is worker's cost for unit privacy leakage, and epsilon is the amount of privacy leakage, which we call privacy budget, guaranteed by the INCEPTION framework. So our design objective for the incentive mechanism is twofold. Our first design objective is to ensure truthfulness, which means that bidding the true value gamma I star, or bidding the true value gamma I star, which is the true interested task set for worker I, and also CIS, which is the worker's true sensing cost, and CIP, which is the worker's true cost for unit privacy leakage, will actually minimize each worker's utility for all possible values of other workers' bids and the privacy budget epsilon. And our second design objective is individual rationality, which means that no worker will receive negative utility after participating. This is actually a crucial property for an incentive mechanism, because otherwise workers will be disincentivized to participate. So we formulate this design of the incentive mechanism as the following optimization program, where PI is a non-active variable indicating the payment to worker WI, and YI is a binary variable indicating if this worker WI is a winner or not. And therefore, the objective function is simply to minimize the platform's total payment. And the constraint is equivalent to that alpha j, beta j accuracy is satisfied for every task tau j. So to simplify presentation, we'll use Qij to denote alpha j minus theta ij squared, and we'll use capital Qj to denote 1 over 2 times log 1 over delta j in the rest of the slides. So, so in short, basically, this optimization program has a nonlinear objective function, and it is NP hard even if PIs are given. And it also have two other inherent constraints, including individual rationality and truthfulness that are not even able to represent mathematically. And basically, what this tells us that this problem is really hard to solve directly. So that's why we propose our own incentive mechanism to solve it. So our incentive mechanism consists of a winner's determination mechanism and also a pricing mechanism. Our winner determination mechanism firstly initializes the winner set as the empty set and initialize the Q prime vector as the original Q vector. So in every iteration, we firstly find the worker WI with the minimum bidding price effectiveness, which is defined as the worker's cost calculated based on this worker's bids over the improvement that this worker makes to the constraint of the optimization program that we have just talked about. And then we'll include this worker WI into the winner set, and we'll remove this worker from the worker set. Finally, we update the residual Qj prime value for every task tau j. So the first takeaway message of this algorithm is that it is monotonic, which means that if a worker wins this auction by bidding a specific set of tasks and a specific bidding price, this worker will also win the auction by bidding a larger set and a smaller price. So second takeaway message about this algorithm is that it actually approximately minimizes social cost. So in our pricing mechanism, we'll first initialize the price vector as a zero vector, and then we calculate the payment to each winner WI. So during the calculation, firstly we run the winner selection algorithm without this specific winner WI, and then we set set as prime as the winner set when this winner WI can no longer be selected as a winner. So finally, we set the price PI as the maximum among those values that satisfy this equation. And basically, what we do is that we ensure the payment to every winner is set as the supremium of his bid to win the auction, which we call critical payment. And this pricing algorithm can also give us a bounded gap between the total payment and the social cost. So we'll also skip all the analysis and directly talk about some results about this incentive mechanism. Firstly, we proved that it's truthful and individual rational. It also has a polynomial time computational complexity, and it has a guaranteed approximation ratio to the optimal total payment. So, then the data perturbation mechanism. So in our data perturbation mechanism, what we do is that we sample a random noise from the Laplacian distribution with zero mean and scaling minus alpha j over log beta j, which is an extension of the Laplacian mechanism utilized in the reference 3. And then we add this randomly sampled noise to the aggregated result to obtain a perturbed result. So basically, this data perturbation mechanism simply adds a carefully controlled random perturbation to the aggregated result to achieve differential privacy without degrading too much the data accuracy. So our results about the data perturbation mechanism are as follows. Firstly, we proved that the proposed data perturbation mechanism gives us absolute differential privacy, with absolute being the maximum among the value minus log beta j over alpha j. And for every task, the proposed data perturbation mechanism also satisfies alpha j, beta j accuracy for the aggregated result before and after perturbation. And then overall, we proved that inception ensures that for every task tau j, it has 2 alpha j, 1 minus beta j square accuracy satisfied for the perturbed result compared to the ground truth xj star. So performance evaluation. Firstly, we compare our PSRC auction with the optimal social cost returned by the VCG auction, where the winner set that minimizes the social cost is firstly calculated, and then the auction will pay every winner according to the VCG payment. This VCG auction obviously offers us a lower bound of the optimal total payment, and it is also truthful and individual rational. Our second baseline to compare with is the bidding price effectiveness greedy auction, which we call BP greedy auction for short. So in this auction, firstly, we sort workers in an ascending order of workers' bidding price effectiveness, and then the workers are selected in this order until every task zero probability is smaller than the predefined threshold. And then we pay every winner according to the pricing algorithm of the proposed PSRC auction. So it is also easily provable that this BP greedy auction is also truthful and individually rational. So we consider 4 simulation settings in this work. The parameters, several of the parameters are chosen from the intervals uniformly random given in this table 1. And actually setting 1 and 2 are smaller instances with smaller numbers of tasks and workers, where in setting 1 we fix the number of tasks and vary the number of workers, and in setting 2 we fix the number of workers and vary the number of tasks. And in contrast, settings 3 and 4 are 2 instances with larger numbers of workers and tasks. So in figure 1 and 2, we compare the platform's total payment generated by our PSRC auction with the optimal social cost and that of the BP greedy auction. So we can easily observe from these 2 figures that our PSRC auction generates a platform's total payment is very close to the optimal social cost and far better than that of the BP greedy auction. And we also compare the execution time of the VCG auction and the PSRC auction. And from this table, we can see that the execution time of the VCG auction grows really fast, and when the number of workers exceed 111, and when the number of tasks exceed 41, the execution time of the VCG auction has already been too long to be utilized in practice. However, the execution time of the PSRC auction remains pretty low over all different numbers of workers and tasks. Then we also compare our PSRC auction with the BP Grady auction in setting 3 and 4, where the size of the problem is too large for the VCG auction to give us the optimal solution in reasonable time. So in these two figures, we also show that our BP auction has a platform's total payment that's far better than the BP Grady auction. So finally, our final performance evaluation is about the accuracy guarantee of our inception framework. Firstly, we compare the MAE, which is the mean absolute error of the aggregated result of all the tasks compared to their ground truth. So we showed that our weighted data aggregation mechanism can have an MAE that is far less than that of the mean and median aggregation. And in figure 6, we also show that the mean empirical error probability after perturbation of our inception framework is pretty small and far less than the required threshold. So in conclusion, what we do in this work is that we provide an integrated design of mobile crowd sensing system framework called Inception that consists of incentive mechanism, a data aggregation mechanism, and data perturbation mechanism. And the proposed framework can approximately minimize the platform's total payment, and it can also satisfy truthfulness, individual rationality, and differential privacy. So these desirable properties are validated through rigorous theoretical analysis and extensive simulations. And the final acknowledgement to make is that this work was primarily funded by the US National Science Foundation Award, Trustworthy Health and Wellness. So this is pretty much about my presentation. Thank you for listening.